in 1999, I was on orbit, and let's see, today's the 21st. So we were getting ready for capturing Hubble. So 1999, this time, we were grabbing Hubble because the gyros had failed such that Hubble couldn't do science anymore. And on the 24th, Steve Smith and I went out and did the final EVA on Hubble, finishing up, a bunch of different tasks. And then on the 25th, deployed Hubble, off as a Christmas present to planet Earth. So I think it's especially fitting that this year, hopefully on the 24th, we launched the James Webb Space Telescope, which on the 24th and 25th will start its series of deployments as a Christmas present for astronomers and humanity in 2021. So it's unfortunate all the folks at French Guiana and at Goddard Space Flight Center and Northrop Grumman and Space Telescope Science Institute and in Europe will have to work over Christmas, but there's no place I'd rather be on Christmas than in space. And I think, if we want to anthropomorphize James Webb Space Telescope, that's where it wants to be too.
When I see the observatory, I was actually fortunate enough to travel down to French Guiana last month with a group of around 20 or so journalists. I think we were the final journalists to see the observatory. It was all folded up as the black colors of the thermal blankets, the purple hue of the sun shield, the gold mirrors. It looks like a Christmas ornament. That's what I thought. And it's very fitting to be launching at this time.
Yeah, my family no longer does Christmas trees, but I should have thought of that. It'd be nice to have James Webb Space Telescope little Christmas ornaments, 3D printed or something like that. I'm sure they're out there.
Yeah.
Well, that's very cool that you got to go down there.
Yeah, it was really, really amazing to get to see it, and to see it all folded up to fit inside the fairing, and just to realize how big it is looking at it in that configuration, and then how big it's going to be when it unfurls that sun shield and the wings open, and when it's really taking science is it's going to look completely different, and
nobody will be able to see it.
Yeah, exactly. Yeah, when it went that fairing, it's the last time anybody's going to be able to lay eyes on it.
Yep. So that's great that you got to see it. Last time I saw it was actually in the clean room at Goddard. I haven't seen it since then.
With the telescope during integration.
Yeah. Yep.
Well, I did want to ask you a little bit, since you do have experience with Hubble, you have an experience in astronomy research. Just your own thoughts on the launch of Hubble. First of all, everyone seems to have a similar but maybe a slightly different answer to this question, and you've probably heard it many times. What types of discoveries or results from Webb are you most excited about seeing?
Well, I look to the commissioning of most observatories, whether ground-based or space-based, where we're advancing, the ability to see the cosmos in some way, whether it's wavelength or sensitivity because of size, or instrument capability that is, an order of magnitude greater than we've ever had before, or even more. That the most interesting thing that James Webb will discover, actually, the most interesting thing that scientists using the James Webb Space Telescope will discover is something that, human curiosity hasn't imagined yet. That said, there are a number of things that I'm personally interested in close to home, one of which is the James Webb Space Telescope will be able to look at the moon Europa around Jupiter with sufficient resolution and capability to see if we see plumes of water coming out as we do on Enceladus. Hubble has been observing Europa pretty consistently for the last decade, and on and off it sees evidence of water coming out, whether it's a cloud of ionized hydrogen and oxygen or little sprites that Hubble seems to see at high statistical significance. But I think James Webb is going to nail it. Now, of course, Europa Clipper will go there. And in about 10 years, we'll have a definitive answer and the ability to actually to do mass spectrometry. But the James Webb Space Telescope can do that remotely because it can, first of all, it has, Hubble-like imaging and in the infrared unique capability, but also spectroscopically, if we see those plumes, it'll be able to give us a hint of what's in it, whether there's organic molecules, for instance. So I'm really excited about that, close to home. And then, of course, the fact that James Webb can peer into clouds of gas and dust, where it's obscured, by scattering of light for Hubble in the visible and ultraviolet, but in the infrared, we can peer into regions where stars are forming and see basically baby solar systems. I think that's going to be very cool. The ALMA Observatory has been able to see disks and planets forming around stars in our galaxy, and James Webb is going to really, give us some great detail on that. And then looking at our own galactic center, a team last year won the Nobel Prize in Physics, including a friend of mine, Andrea Getz, at UCLA, for looking at the motion of stars around the galactic center. And the reason we can't do that with Hubble or many observatories on the ground is because there's too much junk in the way, too much gas and dust in our galactic center. And we have a massive black hole there, is what they've discovered. I haven't really thought about it very much, how much James Webb will be able to do, but as an infrared telescope, it should be able to peer into the center of our galaxy and learn a lot more. There's an enormous amount of science that it will do, studying the flow of gas in and out of galaxies, the formation of galaxies, and there are many people who are very interested in that. But the next topic for me that's of interest is really looking back to the most distant objects, going where no Hubble has gone before, to be able to see the first stars, black holes, and the formation of galaxies, and answer the question of, when did stuff start happening in our universe? It was this, warm and rapidly cooling soup of, hydrogen and helium, and eventually the first stars turned on, and sort of cleared out, the forest floor so that we could start seeing the trees. And we don't know when that was. And because, Hubble has given us a glimpse of these sort of weirdly shaped toddler galaxies, the question is, what were the babies? Did the universe really start with, supermassive stars, very short-lived, that then blew up into supernovas and started seeding the universe with chemical elements that eventually led to us? Or, was it sort of a slow, boring start with little teeny seedling stars that eventually collected into the early galaxies? So we're going to learn something pretty fundamental about, the early days of the universe. Not only the time, when did those things start happening, but also, the morphology of, was it supermassive black holes? Was it stars? Was it both? We know because they're quasars that supermassive black holes form pretty early, but we don't know whether those were the seeds of galaxy formation and structure, or whether it was stars. And then there's the question of 96% of the universe is dark matter and dark energy. Will we learn something really fundamental about the early universe that gives us some idea of what those things might be? And nobody knows. We haven't ever looked there.
This observatory seems like a discovery machine. A lot of NASA missions are focused at maybe answering or trying to answer one or two of those questions. And this is going after a wide breadth of stuff.
Yep. Oh, and I forgot a whole nother field. One of the pleasures of being associate administrator is you get to, based on recommendations from peer review, select missions. And I selected the Transiting Exoplanet Survey satellite in part because it would find targets for James Webb Space Telescope. And so we now have a catalog of nearby transiting exoplanets that the James Webb can now interrogate, and not just finding them, which TESS has done, but now really trying to understand what are the planetary atmospheres like. We know basically that if you look up at the night sky, every star has a solar system around it. And many of those, the planet transits in front of the star so that some of that light gets absorbed if the planet has an atmosphere. And we can then study that using the James Webb and find out, what's the atmosphere like? Is it like the Earth? That would be really interesting. So pretty excited about that.
So a lot of people call Webb the successor, not a replacement, but maybe a successor for Hubble. What benefits does observing in the infrared range bring to astronomers?
Well, I think of it as a partner to Hubble. I'm really excited that Hubble is still operating. Knock on, on Hubble. Knock on Hubble. Anyway, that Hubble's still operating because each wavelength range offers its own unique capabilities. And that's why, we now live in this multi-messenger, we call it, world of astronomy, where you have photons of light, which goes all the way from gamma rays to radio. And each wavelength, we can call it a messenger of some kind of information. But we also have particle astrophysics, where it's actually carried by fundamental particles, like cosmic rays, high energy protons, electrons, neutrinos, and then gravitational waves, which are totally different. And they carry different information about, mergers of black holes and neutron stars and things like that. So we have this, broad cornucopia of wavelengths and particles and fields to study. And the James Webb is in the near infrared to mid infrared. And there are different reasons why we really like that and where it can see things that Hubble can't. From an imaging point of view, the James Webb mirror is obviously much larger. Hubble is 2.4 meters. The James Webb is 6.5 meters. And so you'd think, well, it'll be better pictures. But of course, if you go to longer wavelength, then the diffraction limit is also different. So really, I think the quality of the images, we're going to get Hubble-like images from the James Webb Space Telescope. And that's really exciting because in the infrared, we've never had that before. One of the greatest results of the Hubble Space Telescope, I think, is that it has sort of illuminated the fact that the universe is much more beautiful and rich than we ever imagined, because Hubble now has eyes, instruments that are comparable to what humans see the world around us in. And so when you look at something like, the pillars of creation or the Orion, Great Nebula in Orion, we're now seeing that with the color depth and the richness that we never imagined the universe had. You look up as a kid and what do? You see a lot of little spots of light. And it turns out the universe is much more beautiful than that. James Webb will do that for us in the infrared from an imaging point of view. But from a science point of view, that infrared light allows us to see in regions where we couldn't see before. So when Hubble looks at the Great Nebula in Orion, it sees the glowing hot gas and dust at very high temperatures. But inside of those dust clouds are cooler objects that are emitting in the infrared that Hubble can't see. So James Webb is going to be able to see those early solar systems forming around, baby stars that aren't hot enough yet to produce the ultraviolet light and visible light that Hubble sees. As well, we talked earlier about the first stars and galaxies in the universe. Many of those stars were stars burning very hot, producing ultraviolet light and visible light. But because that light was emitted 13.5 billion years ago, and the universe is expanding, that light gets stretched out. And so that ultraviolet light from the very first stars would now be in the infrared. And so Hubble, even if it were bigger, couldn't see that because it's not an infrared telescope. That's what James Webb will be able to do. And then all those other things in between that I talked about, interrogating exoplanets. The James Webb Space Telescope is not only an imaging telescope, but it's a spectroscopic telescope. And it has the capability to look at a scene and not only image it, but at each pixel develop a spectrum that tells you what the constituent parts are. And whereas Hubble's primarily looking at atoms that are very energetic, where we're seeing an electron jump from one energy level to another and a photon is emitted in the visible range, the James Webb can see some of that, but also, and in particular, molecules that rotate also obey quantum mechanics, of course. And when they change energy states, they emit a photon as well, but this time in the infrared. And so it's actually a molecular detective, if you will, the James Webb Space Telescope. So we're going to be able to study in so-called molecular clouds what they're made out of, or the regions around baby solar systems, or exoplanet atmospheres. And so I find that very exciting. And of course, Europa around Jupiter.
Yeah, in our own neighborhood.
Our own neighborhood, yep.
There won't be an opportunity to send a space shuttle with a team of you and your crewmates up to Webb to service it out at the L2 Lagrange point. So, you know, this whole complex series of deployments that have to go on after the launch, you know, the launch itself is not risk-free. What about that gives you the most pause? You know, you were the associate administrator for the Science Mission Directorate during a key period of development. I'm sure you've studied all of that, had briefings on all of that. What about that whole process is the most, like, I don't know if frightening is the right word, most anxiety ridden for you?
Well, you know, when I took over, you know, management of the Science Mission Directorate and by extension, the James Webb Space Telescope, one of my first responses was, you know, let's put a little grapple fixture, I mean, really small, and some targets on the James Webb, just in case, you know, we have to run it down and give it a little shake to try and deploy it. And I got enormous pushback. The design for the James Webb was incredibly mature, you know, basically, you know, finished, and mass was a concern. You know, they didn't, you know, even though what I proposed was 0.5 kilogram, they said, no, we can't add any mass. And the same thing is true. People were saying, why don't we put some little cameras on to watch the deployment? And the proposal was, we'll put battery powered cameras. So once it's all deployed, you know, within, you know, a few months, those batteries will die, those cameras will cool off, and so they won't be sources, because, you know, anything that's hot in the field of view of the telescope will ruin it. That's why it's going out to the L2 Lagrange point. And it has the big sunshade. We want it to be as cold as possible. But, you know, adding cameras or adding a grapple fixture was something that the project manager said, no, we really can't do that. And I said, well, what's your plan then? And Bill Oakes, he said, our plan is to make sure we design it, test it to the maximum extent possible to make sure it will all work. And we have lots of little micro switches that will tell us what the configuration is exactly. So we don't necessarily need cameras. We can image it on a computer. And while I agree totally that that's true, you know, being visual animals, you know, we like to see things, but we will have those animations. And they have plans where if something doesn't deploy right, where they can, the team will, you know, drive it the other direction and, you know, maybe try and shimmy it with the motors a little bit. So if there are problems, they have some contingency procedures. But, you know, given that there's, you know, 40 different major deployments and hundreds of pulleys and wires, you know, the whole thing makes me nervous, and will until it's fully deployed. Now, we did have some success in that there are small targets on the spacecraft part, the warm part, such that, you know, perhaps in a decade, depending upon how technology marches on, you might be able to send a spacecraft and refuel James Webb. It's not easy. You know, those big sunshade parts are very delicate. You know, we have 5 layers spread out the size of a tennis court with all these little wires. And if you were to zoom in there with a spacecraft, robotic, with big thrusters, and then you brake, the plumes from those thrusters would probably fold up the sunshade. So you have to really be very gentle if we're going to ever refuel James Webb. But the first order of business is to launch it, successfully deploy it, do a decade of amazing science, and then we can decide whether it's worth trying to go up there and refuel it.
The Webb was almost canceled. I think it was proposed to be canceled in 2011 by the House of Representatives. Were you at NASA at that point?
So I was not. I was Deputy Director of Space Telescope Science Institute. And what I would say is that there was wide recognition in 2010 that the funding profile for the James Webb Space Telescope was not adequate to bring it to completion, for a bunch of reasons. And NASA chartered a report that identified those management problems. And in the report, they say James Webb has made amazing technical progress. All of the miracles that have to be solved in terms of, how to pack it into a rocket fairing where it is now in French Guiana on top of the Ariane 5, how to build the detectors that could operate as low as, 7 Kelvin, how to cool those detectors down that cold, how to build optics that live at 38 Kelvin, close to absolute zero, how to build a sunshade that would allow to block the heat from the sun to allow the telescope to get to that temperature, electronics that operate, near absolute zero, all of those kind of things the team had solved. It was a question of the amount of money that was needed in the right years to be able to bring the observatory to completion. When I started at Space Telescope in 2010, the planned launch date was 2014. And there was no way we were going to make that. And so that report said, hey, if Congress can fund it properly, and this is how much it would probably cost, we could launch, as early as 2015, and Congress worked hard on the budget and was able to then predict 2018. And technically, the optical telescope element made all of its milestones. And there's a variety of reasons why we're basically sitting on the launch pad in 21 and not October 2018. But I think there was discussion about whether we should cancel James Webb. And that's a requirement actually in law, that if a project goes over a certain amount or has a certain schedule delay, big projects like James Webb, then Congress has to be notified that would trigger a cancellation review. But Congress was firmly behind this project. It's so important for American science and American leadership, that they decided it was worth funding it. And of course, we're not alone in this. The James Webb Space Telescope is an international project. And so we have commitments to the European Space Agency and the Canadian Space Agency that are integral partners of the observatory, that we would launch this. So.
How much of, given the price tag and how long it took to develop and the scientific promise that's really undisputed, in my opinion, that comes from Webb, all those things combined, how much of NASA's reputation or the NASA science reputation is hinging on the success of this mission?
I think when we had the problem with Hubble in 1990, with the mirror being slightly misshapen, out of focus, I think at that time it was recognized that NASA was in big trouble. We were proposing to build a space station, an international space station. That was the discussion. And there was plenty of talk about, well, if NASA can't build a telescope, right, how can it possibly build a space station? And that discussion turned to, well, if NASA can't fix the telescope, how can we build a space station? And so in 1993, when the crew of STS-61 went up with women and men in white suits to rescue the telescope, I think much of NASA was hanging in the balance. I think now, we've more than demonstrated with 5 successful Hubble servicing missions, 2 very complex rovers Curiosity and Perseverance on Mars, a fleet of Earth science missions, Parker Solar Probe, all of these amazing missions throughout the solar system, around Earth, in astrophysics, that while James Webb is, definitely a flagship premier observatory and very expensive, I think we recognize that rocket launches are risky, the James Webb deployments are risky, but that's what NASA does. We try hard things, and we're very successful at it. But there's always risk, and the public should be cognizant that, instead of 7 minutes of terror, like entering the Mars atmosphere, we're going to have months of terror until the observatory is commissioned. But we have other exciting plans. We have plans to go to the moon, eventually to go to Mars, that are well along. Next year, we'll hopefully see the debut of the Space Launch System and the Orion capsule. I don't know if you've had a chance to see it in the VAB, being there local. So I don't think that James Webb is make or break the way it was for Hubble back in the early 90s.
So, back to the servicing thing before our time is up. Astronauts went to Hubble, you went to Hubble, but it sounds like with Webb, there's not much, external that a spacecraft or astronauts will be able to do. I guess the Webb hugger or the Webb refueler may be a robot and not a human, if there is such a thing. Seeing Webb off for the last time, leaving Earth, what are your emotions right now, seeing that machine set off on its mission?
I'm just really completely excited that it's finally on the launch pad. I'm confident that it will deploy properly, as much as anybody can be, given all the complex deployments. And I'm going to be just incredibly excited to see the first images, the first spectra, in the coming months. And it's a great story. All that said, my opinion is that the next large observatory on the scale of James Webb that we send up, we ought to build in space. Having worked on Hubble, on 3 missions, 8 spacewalks, I'm totally convinced that I could assemble something like James Webb, with spacewalking crew, or robotically. Robotics on Earth and in space are advancing so quickly, that I think it would be much lower risk to build the parts here on Earth, send them up to space, put them together, verify it all works, and then send it off. And in doing that, by making an observatory modular in that way, kind of Lego sets, you would also inherently make it serviceable, so that it could be refueled, so that you could put new scientific instruments in. The one thing, there's no disappointment in it, but the one fact about the James Webb Space Telescope is that it's designed to a 5-year life that we believe we can extend to 10 years. But keep in mind, we're in the 31st year of the Hubble Space Telescope. If it lasts until next April, 32 years. And in large part, the great scientific achievements from Hubble have been due to its longevity, that we've been able to learn how to operate it, that we've put new instruments in it, that have expanded its capabilities, factors of hundreds. And I think future observatories should take advantage of that as well. It's very hard in the infrared because of the requirement to cool the telescope, but not impossible.
Well, John Grunsfeld, scientist, astronaut, former NASA associate administrator, thank you for your time.
Sure, my pleasure.